So good morning, everyone. I want to cover two topics. First, I want to go back to the original theorem of Gorenstein about plane curves, which was one of the inspiration for development of this theory. So you have seen the sources of Gorenstein rings that we have seen so far, how Gorenstein rings were looked at from very different points of view. So, of course, the oldest reference is due to Macaulay. F.S. Macaulay. And he was investigating inverse polynomials. That is, the ring in x1 inverse, x2 inverse, xn inverse. And there is a action of this ring on the polynomial ring. So it's enough to say what is the product of monomials. So if you take a monomial, take two monomials where this is in, suppose this is my S and this is R. And so take this x beta in S and x alpha in R. Then this is 0 if alpha plus beta has a positive coordinate, have a positive coordinate. Otherwise, it is equal to alpha plus beta. So he was investigating Gorenstein rings. He constructed Gorenstein rings using this method. There's a nice paper of Northcott where he explains this approach. It is quite easy to understand. And he shows that S mod R, okay, is the injective hull of R. Okay. The other source of Gorenstein rings came from Northcott trees themselves. And this I discussed in the first lecture. So they were investigating number of irreducible components of ideals generated by system of parameters in Cohen-Macaulay local rings. And so they linked it with the dimension of the socle. Okay, if you take a system of parameters in a Cohen-Macaulay local ring and then go mod x bar, then this is an Artin local ring. This is an Artin local ring. And you can construct the socle of this Artin local ring. This is an essential extension always. And this is a vector space. This socle is a K vector space. K is the residue field of this. And the dimension of the socle of R mod x bar is equal to number of irreducible components of x bar. And it is also equal to, we have seen that this is also equal to dimension over K of x d r kr. So it is independent of the system of parameters chosen. So any and then they investigated the Cohen-Macaulay rings where every system of parameters is irreducible and found many properties. This was the second source. The third source came from Hyman Bass, and he was investigating rings of finite injective dimension. Rings of finite injective dimension. So just around that time, regular local rings were characterized by this property that these are exactly the rings where the residue field has finite projective dimension. So therefore, it was natural to investigate modules which have finite injective dimension, yeah, or rings which have finite injective dimension. So for Hyman Bass, rings of finite injective dimension are Gorenstein rings. And we have seen that the classical definition of Northcott-Rees and Hyman Bass definition of Gorenstein ring, they are one and the same. And this was first pointed out by Sayre, who proved that suppose R mod I is Gorenstein and R is regular local ring, and height of I is 2, then I is a complete intersection. I is generated by 2 elements. Okay. This also we have seen. Yeah, we have proved Sayre's theorem already. The fourth approach was due to Grothendieck. So Grothendieck looked at rings which are quotients of regular local rings. So in yesterday Professor Patil's lecture, you have seen he stated, but he will prove, I think, next time, that any complete local ring is a homomorphic image of a regular local ring. Yeah, and we have seen that the Gorenstein rings, if you take a local ring which is Gorenstein, its completion is also Gorenstein. But we characterized the Gorenstein property under flat local homomorphisms. Yeah, so if you look at R to R completion, this is a faithfully flat extension, and we saw that the base, this ring is Gorenstein if and only if base is Gorenstein and fibers are Gorenstein, closed fiber. But the closed fiber in this case is R completion over MR completion, and this is equal to R mod M, which is a field. So fibers are clearly Gorenstein, and so Gorenstein property of R and R completion are equivalent. And by Cohen structure theorem, whose proof we will see, complete local rings are homomorphic image of regular local rings. Yeah. So to test Gorenstein property, we might as well write the ring as a quotient of regular local ring. Yeah. So suppose that dimension of S is equal to N and height of I equal to H, and R is Cohen-Macaulay, and R equal to S mod I is Cohen-Macaulay. Gorenstein rings have to be Cohen-Macaulay. So in order to investigate when R is Gorenstein, we assume that R is Cohen-Macaulay. So S is Cohen-Macaulay, but now this S is regular local ring. So projective dimension of S mod I plus the depth of S mod I is equal to dimension of S, which is N. And S mod I is Cohen-Macaulay. So this is equal to dimension of S mod I. And therefore project dimension of S mod I over S is equal to N, that is dimension of S minus dimension of S mod I. And since S is Cohen-Macaulay, it is catenary and equidimensional. So this difference is height of I. So S mod I as an S module has projective dimension equal to height of I. And so we can construct a minimal free resolution of length H. Okay, can construct minimal free resolution of length H. And now look at the X modules, Xi, S of S mod I and S. So this is 0 if I is less than depth S minus dimension of S mod I. But S is regular local ring, so this is dimension of S, and so this is equal to height of I. Yeah, this difference is H. So below S they are 0. Yeah, above H also they are 0. Yeah, so X S 0 S mod I S equal to X H minus 1 S mod I S. These are all 0 modules. Okay, and we have H at X. Yeah, can anybody tell me why this X is non-zero? Nikhilesh?
Sir, height of I is H, and so this beta H is non-zero, sir, I think.
Yeah, so what is the reason?
It is Gorenstein.
Well, no. Even if S mod I is Cohen-Macaulay, this H at X will be non-zero.
Because height I is grade I.
Right. The annihilator of the first module contains a regular sequence of H, length H, because grade of I is height of I in all Cohen-Macaulay rings. S is regular local rings, it is Cohen-Macaulay. Yeah, so annihilator of the first module contains a regular sequence of length H on S, right? On the second module, annihilator of S mod I contains a regular sequence of length H. So this is non-zero. But the later X's are 0. This is 0 for all I bigger than H. Yeah. Do you see that? Does anybody see why the later, Xi for I bigger than H, they are 0? Do you recall a formula where supremum of Xi Mn, where Xi Mn is non-zero, was looked at? Remember this formula, depth of n. Suppose you have a local ring and M and N are finitely generated. Depth of n plus supremum of I, so that Xi R Nm is not equal to 0, is equal to injective dimension of M. Remember this formula? So can you see using this formula that I at X is 0 beyond H?
Sir, projective dimension of S mod I is H. So for I greater than H, the X ties will be 0.
Okay, that is one way, right? But do you see how to use this formula? We will use this many times. Can you see this from using this formula? What should you put as M? What is the module which has finite injective dimension in this setup?
That is R.
S.
Oh, sorry, S.
Yeah. So take M equal to S
Yes.
and N equal to S mod I.
S mod I.
And S mod I is कौन Macaulay? So depth of S mod I. Depth of S mod I is dimension of S mod I.
Mod I N minus H.
Right. So that is another way to prove. Yeah.
Yes.
So you're right, because project dimension of S mod I is H. X I beyond S, they are 0. Below S, they are 0 by Ishebek theorem.
Yes.
So among all the X I, there is only one non-vanishing X. Yeah. This is the only one non-vanishing X. Yeah. This is the only non-vanishing X. So now look at the resolution. Look at the resolution. We have projective resolution or free resolution, minimal free resolution of S mod I. So 0 to S, beta H is H. I mean, sorry, the length of the resolution is H. So I have this Betti number beta H, then S beta H minus 1, then S to S mod I to 0. So this is the only non-vanishing X. So in order to calculate this X, I can take either an injective resolution of S, which exists, right? What is the injective dimension of S?
N.
It is dimension of S, right? Injective dimension of S, because S is Gorenstein. Its injective dimension is dimension of S. So we could either consider a minimal injective resolution of S, okay, which we have not discussed, okay, or we can take this projective resolution of S mod I and then calculate the cohomology at this spot. So apply Hom S dash S. This is a contravariant, left exact contravariant functor, and the right derived functors. They are all the HF text. So when you apply Hom dash S, okay, then this S is the ring. So suppose I put N here, then I will denote Hom S NS as N star, the dual of N. Okay. So therefore we will get 0 to S star, right? This will reverse. This sequence will reverse because this is a contravariant functor, and then S star beta 1, S star beta H to 0. This is the complex, yeah, whose cohomology gives us all the X I. But there's only one non-vanishing X I, and that will be at this spot. So therefore, suppose this map is phi H, okay, and this map is phi H minus 1, okay. Then the map from S star beta H minus 1 to S star beta H, that will be phi H star, okay. So when you take the dual, the matrices of the maps in the minimal free resolution get transposed. Yeah. So these phi H minus 1, etc., they are represented by some matrices because these are maps between free modules. So they are represented by some matrices whose entries are in the maximal ideal. And when I take the dual, okay, when I apply Hom dash S, then this sequence gets reversed and the matrices get transposed. Okay, so we understand this minimal resolution, and all the cohomologies are 0, except at this spot. At this spot, to calculate the cohomology, we will take the co-kernel of this last map, and that is the HF text. Okay, so co-kernel of phi H star, okay, that is the HF text. Right. So let me call this as 1, and this has 1, and this has 2. So I had a minimal free resolution of S mod I, and this number 2, do you see that this is a minimal free resolution of the HA text? Number 2, because only at the last spot, the cohomology is non-vanishing. And so when I put the co-kernel, I will get minimal free resolution of HA text. Okay. So what is the number of generators of HA text?
Beta H minus 1.
Beta H. Right?
Oh, yes, sir. Beta H. Yeah.
That is beta H. Okay. That is beta H. So the last Betti number in the minimal free resolution of S mod I is the minimum number of generators of this module. And we have proved before that S mod I is Gorenstein. S mod I is Gorenstein. If and only if, what was the condition? Do you remember? Beta H is 1. Yeah. So if I know the Betti numbers of S mod I know the Betti numbers of HA text of S mod I S. They are reversed. Yeah, the Betti numbers of HA text of S mod I comma S are same as the Betti numbers of S mod I, but in reverse order. Okay, and S mod I is Gorenstein. If I look at beta S, that is equal to 1. So this module seems to detect that when S mod I is Gorenstein, right? Its minimum number of generators is detecting whether S mod I is Gorenstein. So Grothendieck defined this as the canonical module. This is the definition due to Grothendieck. The canonical module of S mod I is defined to be HA text of S mod I S. Okay, that is the canonical module, and so by this argument, the canonical module of S mod I is cyclic if and only if S mod I is Gorenstein. So this cohomology module seems to provide an obstruction to a ring being Gorenstein or not. Yeah. So this is what we will study. First, I will talk about original theorem of Gorenstein, and then we will take up a systematic study of the canonical module. And the approach that I will follow is axiomatic, more or less axiomatic. And from some axiomatic characterization, it will come out that this is the canonical module of S mod I. Okay, HA text of S mod I S. Okay. So this is, if you know how to calculate minimal free resolution, you can detect when S mod I is Gorenstein. And that's one of the reasons why people try to construct a minimal free resolution, because it gives information on S mod I. Okay, any questions so far? Are you following? It's too late to ask. Any
well, can you just remind why this beta H is 1? I mean, I attended that lecture, but at the moment I am forgetting this Gorenstein, if and only if beta H is 1, came from...
it came from the Sokal dimension.
Sokal dimension. Okay.
Sokal dimension should be 1, and the change of ring principle for HA text, you can reduce the HA text. Okay. So I has a regular sequence of length h. So suppose x bar is that regular sequence of length h. Then by change of ring principle for x, okay, this x HA text is equal to Hom this is equal to S mod X, S mod I, S mod X. Okay. So, but this is equal to X colon I over X.
Okay.
Okay, and this now S mod X becomes so this is the module, and the length of this module is equal to beta H.
Good. That was also a calculation.
Right, it's a calculation of S at X, and this the S mod I is Gorenstein if and only if this length is 1. There was another exercise. Okay. Yeah. Okay, so let us. So I want to now go back to the Gorenstein's theorem. Okay, this I wanted to do it earlier, but let me do it. Time is running out. So I want to discuss this one of the initial sources of Gorenstein rings, theorem of Gorenstein. That was in his thesis. Gorenstein was student of Zariski, and after his thesis, he quit algebraic geometry and started working on finite group theory. And he led a huge research program on classification of finite simple groups. Okay, but this is what Gorenstein did in his thesis. So he was concerned about plane curves, properties of plane curves. So take K is a field, and take a irreducible polynomial representing a plane curve. So C is the plane curve defined by this polynomial. Okay, and the coordinate ring of C, the affine coordinate ring of C is simply Kxy over Fxy. And assume this is irreducible. So therefore, Kc is a one-dimensional domain, and it is Cohen-Macaulay. So if I take any maximal ideal of Kc, then this maximal ideal of Kc comes from maximal ideal of Kxy. Looks like this. And so the local ring at this point, local ring of C at the point represented by M, okay, is simply the localization at N of this ring. But then this is regular local ring going mod a non-zero divisor. Regular local ring is Gorenstein, and this and we have proved that Gorenstein ring mod a non-zero divisor is a Gorenstein ring. So this is a one-dimensional Gorenstein ring. Okay, this is a one-dimensional Gorenstein ring. And if you study Gorenstein rings in some more, you will see that Gorenstein property often exhibits certain kind of symmetry. And this symmetry depends on the situation that you are in. And Zariski was aware of this symmetry in this situation. And he had an inkling that the phenomenon that Gorenstein observed has to do with Gorenstein rings, but this was not done in his thesis. What he observed was the following. Okay, so let me to illustrate this, I will take an example. Take Fxy equal to the following curve, x7 minus y cube. So this is a highly singular curve okay, x7 minus y cube. And the local ring at the origin of this curve is Gorenstein, but it is not regular because this is not a smooth point. Yeah. So when I look at kxy over fxy, x7 minus y cube, this is isomorphic to k. Okay, I can map x to t cube and y to t7. Okay, and this is a one-dimensional ring. Its integral closure is kt. So the kernel is a height 1 prime ideal in kxy. Kxy is a UFD. So height 1 prime ideal is principal. But this polynomial is irreducible. This is an irreducible polynomial. In fact, if I take two co-prime integers, then xm minus yn will be always irreducible. Okay, so this is irreducible polynomial. So this is the kernel. So therefore, the coordinate ring of the curve, okay, is isomorphic to this kt cube kt7. Okay, and the t belongs to the quotient field, and therefore kt is the integral closure. This is the integral closure of kt cube t7. Right, t7 or t6 is in the quotient field, and this is an integral extension. So this is the integral closure of kc. And obviously, this is a finite module. Okay, this is a finite module. Let me write this rather than writing kc as r. This is a finite module. Right. Now look at the following ideal, which is called the conductor of R. Is all elements in R bar. This is R bar. Take all elements in R bar, so that R times all elements in R, so that R times R bar is contained in R. Okay, you can think of this as the annihilator of the R module, which is R bar over R. Yeah. Now this is an ideal in R as well as R bar. It is common to R and R bar. In fact, this is the largest common ideal of R and R bar. This is a very, very important ideal. Okay, called conductor. That's why it's called conductor. It is conducting elements from R bar into R. That's the reason why it is called conductor. So in this case, let us see the we have the ring R bar, which is kt. Okay, R bar is kt, and R is k t cube and t4. I mean t7. And inside R, we have the conductor ideal. Okay. All these are k vector spaces. All these are k vector spaces. Okay. The conductor is a zero-dimensional ideal. R is one-dimensional, and the conductor you can check. Can you tell me an element in the conductor? Can anybody tell me an element in the conductor?
e to the power 6.
T to the power 6. There is a problem. T to the power 6. Does it multiply t square into R? Do you see T8 is in R or not? T8 is not in R, right? Let us list. R is a vector space. The basis of R is a vector space. Okay. Okay, so 1, 1, then t is not there in R, t square not there in R, t cube is there. Okay, now these are not there. These powers of t are not in the conductor. T4 is in R bar, and T4, is it there in R? In R? No, it is not in R. Okay, it is also not in C. T5, T5, T5 is not in R. Therefore, it is also not in C. T6, T6, T6 is in R. T6 is in R. Okay, but it is still not in C. T6 is not in C. Do you see that T6 is not in C? Because T6 times T square is T8, and T8 is not in R. So T6 is not in the annihilator of R bar over R. T7. Okay, T7 is very much there in R. But is T7 in the conductor?
No, T8 is not there.
T8 is not in R, and therefore it is also not in the conductor. T7 is also not in the conductor. You see, T9, T9 is in R, of course. T cube is in R, so T9 is in R. But T9 is not in the conductor. Do you see that?
It's t to the power 11.
Exactly. Yeah. So T9 is not in the conductor. So now look at T10. T10 is in R and R bar. Okay. What about T10? Is it in the conductor?
Yes, it is.
Hmm?
It is.
No,
No, T11 is not there. No.
Sorry.
Yeah.
T11
T11 is not there. No. T11 is not in R. So T10 is not in the conductor. So we have to still find an element in the conductor. Okay. What about T11? T11 is in R or not? Not in R. T11 is not in R. 11 can't be generated by the semi-group 7, and 11 does not belong to N3 plus N7. Okay. But now we hit an element T12. Okay. What about T12? That is in R. T cube times to the power 4, right? That is in R. And it is also in the conductor. Everything after that is here. Okay. So this is the smallest power of T, which is in the conductor. Okay. Now, what did Gorenstein observe? Gorenstein observed that, look at R bar over R. This is a K vector space. What is its dimension? Can you tell me dimension of R bar over R? Elements in R bar which are not in R, right? What are the powers of T? How many powers of T are in R bar which are not in R? 1, 2, 3, 4, 5, and 6, right? 6 powers of T were in R bar, they were not in R, and beyond T12 onwards, everything is in R. So this is 6, okay? But let us look at the dimension of R over C. How many powers of R, how many powers of T are in R which are not in C? Six, right? 1 T cube, T6, T7, T9, then T10. So this is also 6. Okay, so there is a symmetry here. R bar contains R, contains C, and the quotient of R bar over R and quotient of R over C, they have equal length. So this is Gorenstein's theorem. This is certain kind of symmetry. Okay, so Gorenstein proved that if you take any plane curve and take the local ring at any point of the plane curve, then dimension of R bar over R is always dimension of R over the conductor. This was Gorenstein's theorem. And then there was a student of Zariski after Gorenstein by name of Rosenlicht. I think he took to number theory. Dipendra Rosenlicht.
Yeah, very famous name, number theory. Yeah, some kind of algebraic geometry slash algebraic number. Yeah.
He is the same Rosenlicht, and he generalized this theorem of Gorenstein to complete intersection. Gorenstein's theorem is true for complete intersection curves. That is, take polynomial ring in n variables and then take an ideal generated by this. This is a regular sequence. So this dimension is 1. So this corresponds to a curve, and Gorenstein's theorem is true for this curve also. This is the coordinate ring of that curve. Localized at any maximal ideal, I get a one-dimensional Cohen-Macaulay local ring, and one can prove exactly the same result. Okay, so we will prove. We'll prove Rosenlicht's theorem. And of course, it implies Gorenstein's theorem, because Gorenstein's theorem is for irreducible curve defined by one equation in the plane. Okay, so Rosenlicht is certainly more general than this. So we want to prove that dimension of R bar over R is dimension of R over C when you localize at any point. Okay, when you localize at any point. But when you localize at any point, what you get, okay, any maximal ideal, what you get is a local ring of this type. Okay, local ring of this type. Now this is Gorenstein ring, because this is localization of regular local ring. So this is Gorenstein, and this is a regular sequence of length n minus 1 inside a Gorenstein local ring. So this is Gorenstein ring. Okay. Yeah. So what we have is a one-dimensional Gorenstein local ring, which is a homomorphic image of a regular local ring. And we want to prove that these rings do satisfy Gorenstein's theorem. That is, dimension of R bar over R is same as dimension of R over C. Okay, so that's what I want to prove. Any question? Okay, now local rings are local rings on some irreducible component always. Okay. You take a curve, it splits into irreducible components, and a point will lie on some irreducible component. So we might as well assume that we have a regular local ring, and I have a prime ideal, so that S mod P is a one-dimensional Cohen-Macaulay local ring. Okay. So we can prove the following result, and Rosenlicht's theorem will be a consequence. So let S be a regular local ring. Regular local ring of dimension D. and P is a prime ideal, and height of P is D minus 1. Okay, and R is equal to S mod P. So local rings on these curves in affine n space, they are of this type. Okay, R equal to S mod P, where S is a regular local ring and P is a height codimension, the height D minus 1 prime ideal in S. So this is certainly Cohen-Macaulay. Yeah, this is certainly Cohen-Macaulay, and let R bar be the integral closure in its quotient field. Okay, and C be the conductor. Okay, then length of R bar over R is equal to length over R over C. Okay, so I'm not even assuming that the ring contains a field. Yeah, this is independent of the whether it is equicharacteristic or non-equicharacteristic. I have any regular local ring mod prime ideal, so that S mod P is one-dimensional, and it is one-dimensional domain. So it is certainly Cohen-Macaulay. And look at R bar over R and take its annihilator. Okay, take its annihilator. Okay, then this is true if and only if R is Gorenstein. So it characterizes one-dimensional Cohen-Macaulay domains which are Gorenstein. This equation. It is some sort of symmetric equation. Symmetry between R bar, R, and C. Okay. So Gorenstein, of course, proved only one direction. And Zariski had some inkling that actually it is a characterization of Gorenstein local rings. And he asked Kunz. So Kunz proved this direction. This is due to Kunz. And there's a beautiful paper of Kunz. I suggest that you read that. This is published in 1969. It's called the value semigroup. Value semigroup of one-dimensional Gorenstein ring. So in that example where we had K, T, Q, T7, we were actually analyzing the semigroup which is generated by 3 and 7. And there is a concept for numerical semigroups called symmetric numerical semigroup. And Kunz proved that the semigroup, if I take this ring generated by powers of T, then he characterized when it is Gorenstein. It is Gorenstein if and only if the semigroup generated by the exponent is a symmetric semigroup. And that symmetry translates into this property. Length of R bar over R equal to length of R over C. Okay. So I will not give Kunz's proof. This is classical, completely classical, no homological algebra. He uses the classical definition because it is in 1961. He uses the classical definition of Northcott and Rees that a local ring is Gorenstein, one-dimensional local ring is Gorenstein if you take any non-zero divisor, then it is an irreducible ideal. So he uses that definition to prove both the directions of this characterization of one-dimensional Gorenstein rings. So I will give a much shorter proof using the X. Okay, we want to practice with X as much as possible. So I will give a homological proof.
Jugal, I presume that not only are the lengths same, but there is some R structure which is preserved.
Yeah. So that will come out in the proof.
That they are not isomorphic as R module, but maybe they are dual to each other in certain sense.
Yeah, exactly. They are dual.
Yeah.
R bar over R, we will see representations of R bar over R and R over C in terms of X modules, and then using mathless duality, it will become clear why the lengths are equal.
Good.
Okay. So what we will do, we will find X1 of R bar over R, okay, in two different ways. And those two ways will lead to these two modules, R bar over R and R over C. And you will see why the lengths are equal. Okay. Now, R bar over R is an Artinian R module. Because conductor is a height 1 ideal. I'm assuming that R is not R bar. We do have a singular point. Yeah, I have a curve and I have a singular point. This is a local ring of a singular point. So R bar is not equal to R. Okay. So, but conductor is the annihilator. Conductor contains a non-zero divisor because R is a Cohen-Macaulay domain. It contains a non-zero divisor, and therefore the annihilator of R bar over R is M primary. Annihilator of R bar over R is M primary. Okay. But this is M primary, and but the annihilator of this is contained in the annihilator of the X. So these X modules are also finite length modules.
Sir, what is I?
R bar over R. There is no I.
The annihilator of R bar module.
R bar over R.
Okay, that is R.
Yeah, sorry. Yeah. Okay. So this is Artinian module. It is of course finitely generated. Yeah. So we will find the length of this module. We will calculate X1 of R bar over R and find the length. Okay. Now this X1, so just focus on X1. There are two ways of doing this. R is a one-dimensional Gorenstein local ring. So I am proving one direction, that R assuming that R is Gorenstein local ring. So this injective dimension of R is 1. Yeah. Gorenstein local rings have finite injective dimension by Gauss, and it is equal to depth of R. Depth of R is 1 because R is Cohen-Macaulay. So injective dimension is 1. So I can take an injective resolution of R, which has length 1, and apply Hom R bar over R dash to calculate this X. Okay. Or the other way around is to look at some exact sequence which is relating R and R bar. And of course, we know this exact sequence. So we will calculate this in two different ways. Okay. So let us look at the injective resolution first. Okay. Let's look at the injective resolution. So R is an integral domain of dimension 1, and its quotient field is an injective module. It's a divisible module, so it is injective, and because this is an essential extension, it will embed into the injective hull of the residue field. So this is an injective resolution. Yeah, this is an injective resolution. And so once I have injective resolution of R, then I should apply Hom R bar over R dash. This is a covariant functor. Okay, this is a covariant functor. So the direction is preserved of this exact sequence. Okay, so when I apply Hom R bar over R to this, then I get 0 Hom R R bar R Hom R bar R to quotient field, and then Hom R bar over R injective hull of the residue field, and then I get my X modules, X1 R bar over R, then X1 R bar over R K, and then X1 R bar over R E. And then I get 0, right? Because injective dimension is 1. So it goes up to X1. Now let's look at these modules. Hom R bar over R. What can you say about this? Is this 0 or not? Hom R bar over R. The annihilator of R bar over R, does it contain a non-zero divisor? Annihilator of R bar over R is the conductor. And conductor contains a non-zero element, non-zero divisor, because R bar is not R. It's a non-zero divisor on R. So whenever the first module has a non-zero divisor on the second module, what is its Hom?
It is 0 then.
Exactly. This is 0. This is 0. Okay. Now, what about this Hom? Hom R bar R, comma K. On K also, the conductor elements are non-zero divisor on K also, right? They can't kill elements of K. This is 0. Right? What about this module? X1 of R bar or R E. Or X1 of R bar or R comma K. Okay. Look at this module. X1 R bar R K. What can you say about this? K is an injective R module. K is divisible R module, right? So it's an injective R module. And when you have injective R module here, this is 0. All the higher X are 0. When you take X I of M comma N, where N is injective, all the higher X are 0. So this is 0. So I'm just left with X1 R bar R is isomorphic to Hom R bar R E. Okay. Now here, this proposition you can prove yourself that if E is the injective hull of the residue field, then the length of M dual R ME. Suppose M has finite length. If this has finite length over R, this length is same as length of M. Okay. So I get one formula for X1. So this tells me by using this proposition that therefore the length of x1 r bar over r is equal to length of r bar over r. Okay. Now I have to capture length of r over c. So I have captured the length of r bar over r in terms of length of x1 of r bar over r comma r. Okay. Now we want to look at the other way of computing the x. So I already used injective resolution of r to calculate this x, and now I will not use injective resolution of r. I will just work with some exact sequence involving r and r bar. So take r to r bar, and then r bar over r. Let us call this as d. D equal to r bar over r. Okay, I have this exact sequence. So so this will give rise to long exact sequence of the X modules. Yeah, long exact sequence of the X modules. Okay. Yeah, so apply hom dash r. This is a contravariant functor. Okay, so therefore we will get the following long exact sequence: hom r d r hom r bar r hom r then hom r. I mean, sorry, x1. Now we are at the x1 level. x1 r dr x1 r r bar r to x1 r to rr to 0. But r is injective, so this is 0. That is 0, right? Now, so which one of these modules are 0? Let us see that. So this is hom rr. Hom rr is just r. This is just r. Okay. What is hom r bar comma r? Can anybody tell me what is hom r bar comma r? I mean, how do we produce homomorphisms from M to R? R bar to R. How do we produce homomorphism? I will have to take an element in R and look at its multiplication map, but then that element has to multiply elements of
Conductor
R into R, right? What did you say?
Conductor ideal.
Exactly. That is the conductor. This is our conductor. And what about hom dr? Hom dr. D is r bar over r. Annihilator of r bar over r contains a non-zero divisor. So by the same reasoning, this is 0. So I have this exact sequence: 0 to c to r to x1 r bar r, and so what about this x1? There's again 0 because r is injective module. What is the reason for x1 of r bar r to be 0? Once I prove that this is 0, it will follow. X1 of r bar r. How to see x1 R, R bar, R. Does anybody see that this module is 0? R, I'm assuming R is injective. Okay, R is injective. I mean, R is Gorenstein. R is not injective. R is a Gorenstein local ring of dimension 1, so it has finite injective dimension. Yeah, we have a nice tool to detect the last I, so that this is non-zero. Yeah, and that is given by this formula: depth of n plus supremum of I, so that X I R nm is not equal to 0, and this is equal to injective dimension of m. Suppose I have a module of finite injective dimension, then we know that it is equal to depth of R. Okay, in our case, this is equal to 1. What should I take n? N to be R bar. Yeah, what is the depth of R bar as a R module? Depth of R bar as a R module?
It's positive.
1.
1, yes.
R is one-dimensional Cohn-Macaulay domain. R bar is also one-dimensional Cohn-Macaulay module over R. It is finitely generated. Yeah. So its depth is 1.
Yes. Yes.
So that means this supremum is 0. That means beyond 0, all the X-I modules vanish. Whenever I take a one-dimensional Gorenstein local ring, then it will say that for all finite R modules, this is 0 for all I bigger than or equal to 1. So that gives me this exact sequence: 0 to C to R to X to 1, R bar over R to 0. And therefore, X to 1, R bar over R. Is isomorphic to R mod C. And therefore, the two lengths are same.
How did you get this sequence? What happened to X1 dr?
X1 dr.
Yeah, so you look at the sequence, like there's X1 dr in between.
Just one moment.
D is R bar over R.
D is R bar over R.
Okay.
Right. So we are computing X1 dr. This X1 R bar R is 0 by this formula about depth n plus supremum, right? So X1 of R bar over R comma R is computed as quotient of R by the conductor. And so we calculated in the earlier way of computing X1, we showed it is form of R bar over R, comma injective hull, but that length is same as length of R bar over R. And so we get this formula. So this is the Rosen-Licht's theorem proved in much more generality for quotients of regular local ring, which are one-dimensional Cohn-Macaulay domains. So it covers both theorems of Gorenstein and Rosen-Licht. Any doubts on this proof? Any statement which is not clear? So homological proofs are, they work like a machine, and you get beautiful theorems like this. We just computed X1 in two different ways. We don't know what we were getting. but it is just, we have to understand which X modules are non-vanishing and which ones are vanishing. And this gives this symmetry condition, Gorenstein's theorem. Okay. Yeah. So I have proved only one direction. That is, if it is Gorenstein, then length of R over C equal to length of R bar over R. But this property characterizes one-dimensional Gorenstein local rings also. Okay. So I want to develop enough properties of canonical module, this growth index approach to Gorenstein rings, and come back in the last lecture. Next week, I will give 2 lectures and try to prove the converse of this theorem. Okay, that this is a characterization of one-dimensional Gorenstein local rings, which are domains. Okay, so I want to now begin developing the theory of canonical modules. I'll do some preliminaries. I think I have about 15 more minutes. Okay. Canonical module. Right. So, so we will study these 4 Cohen-Macaulay local rings. Let Rm be a Cohen-Macaulay local ring and a module, a finite R module, finite R module, C for canonical is called a canonical module for R if it satisfies 3 conditions. C is a maximal Cohen-Macaulay module. That means its depth is dimension of R. Depth of C is dimension of R, maximum possible. Okay, so C is a maximal Cohen-Macaulay module. Second, injective dimension of C is finite, and we know that if it is finite, then it has to be depth of R, and depth of R is dimension of R. So C has finite injective dimension. C is finitely generated, and C is maximal Cohen-Macaulay module. And there is one more condition: the type of C is 1. So type of C by definition, it is equal to dimension of X D R K C. Okay. So if C is the ring R, then this is really the Socle dimension. By change of ring principle of Ries, this will be the Socle dimension. So type is dimension of the largest X, only non-vanishing X of Kc, and this dimension is 1. So in some sense, these are the simplest Cohen-Macaulay rings you can imagine, because the complexity among all the X ties of Kc, yeah, this is the only non-vanishing X. Okay, and its dimension is the measure of complexity of this ring, and when it is one-dimensional, then we must get the best kind of rings, and these are the best modules, and so these are called canonical modules. Now we will prove that canonical module, if it exists, it is uniquely determined up to an isomorphism. Any 2 canonical modules. So this is one of the theorems that we will prove. Any 2 canonical modules of R are isomorphic. And we will prove that the Gorenstein situation, that if ring is Cohen-Macaulay ring is quotient of a regular local ring by a height H ideal, okay, then the canonical module exists, and it is in fact hth x of S mod I S. Okay, so Grothendieck used this module to define Gorenstein rings. Yeah, that if this module is isomorphic to S mod I, then S mod I is Gorenstein ring. That was the definition of Gorenstein, and we will see that canonical module of S mod I, where S is a regular local ring and I is a height H ideal, is exactly the only non-vanishing x of S mod I comma S, which is the hth x. Okay. So these are the two results I want to prove. It will require several preliminary steps. Okay. Okay. So you have to and then using these, I will come back to Gorenstein's theorem that one-dimensional Gorenstein rings can be characterized by the equality of length of R mod C and length of R bar over R. Okay, so that is the plan. So remaining time, I will prove one preliminary result, and then we will stop. Okay, so our approach to study of canonical modules will be sort of by induction, because these are maximal Cohen-Macaulay modules. So when I take any maximal regular sequence in the ring, in the maximal ideal, it is going to be a regular sequence on C also, on the canonical module, because this is a maximal Cohen-Macaulay module. Yeah. So we will see how canonical modules behave when we go mod a non-zero divisor. Okay. When we go mod a non-zero divisor. And that is the whole trick, how the X modules behave when you go mod a non-zero divisor, and how can we lift the uniqueness of a canonical module by applying induction on the dimension. Okay. Yeah. So this is the first lemma, that suppose I have a Noetherian local ring. Take any Noetherian local ring. Noetherian local ring with residue field K, and M and N are finite R modules. Okay, and X bar is a regular sequence on N. X bar is N regular sequence. And phi from M to N is a module homomorphism. Okay. Now, if phi bar from M mod XM to N mod XN is an isomorphism, then phi is an isomorphism. Okay, we will ultimately use it to prove uniqueness of the canonical module of two isomorphism by going mod, by applying induction on the dimension, and dimension can be reduced by going mod regular elements. So that's the technical lemma that we will need. So proof, let's see a proof. So suppose K is the kernel. Suppose K is the kernel and C is the co-kernel. So I want to show that K and C both are 0. Okay. I want to see K and C are both 0. So now, but we have information on phi bar. So when I take phi bar, then I get phi bar is obtained by tensoring with R mod X bar. To tensor with R mod X bar, this is a right exact functor. Okay, so therefore I get 0 to K mod XK, okay, to M mod XM. I can take just one element and prove the theorem for one non-zero divisor. The theorem will follow, okay, by induction on the length of the regular sequence. So I can just take one regular element and prove the theorem. Okay. Yeah. So this when I take C mod XC, okay, C mod XC is 0 because phi bar is an isomorphism, and C mod XC is 0. So by Nakayama lemma, C is also 0. So I get this exact sequence. Okay, I get this exact sequence because X is n-regular. Remember in the very first lecture, I showed you when I had a 4-term exact sequence and an element is regular on the last module on the right, then I can tensor with R mod X and get an exact sequence. So this is an exact sequence, but phi bar is isomorphism. So this K mod XK is 0. So by Nakayama lemma, it implies that K is also 0. Okay. Right. So if I have a regular element on N, and after go mod a non-zero divisor on N, I get a isomorphism, then original map is also an isomorphism. We will use this repeatedly. Okay, next. Yeah, maybe I don't think I can finish the proof of next result, and this is almost 11:25. So let me stop here, and I'll continue next week.